This video is about applications using rational equations and proportions. Now that we've done some of the algebra involved with rational equations and expressions in recent topics, we're going to apply that to some word problems or story problems that may require it. So let's go through several examples. The first is this. In still water, a boat averages 18 miles per hour. It takes the same amount of time to travel 33 miles downstream with the current as 21 miles upstream against the current. What is the rate of the water's current? Now, as we've already seen in word problems previously, one of the first key steps is to understand what kind of problem we're dealing with. There are several kinds of problems that may involve, certain formulas in maybe geometry or physics, and understanding what we're working with is really step one. Now, this kind of problem is what we can refer to as a distance equals rate times time problem. We've seen a little bit of this already, where this is just a general physics formula. Distance equals the product of rate and time. And as you can see in this problem, you're dealing with distances like miles, and then rates like miles per hour, and time like hours. So this is how we can identify the type of problem. Now, to handle this type of problem in particular, we prefer to use a chart to stay organized. Now, you don't have to use a chart of this type, but it's just a pretty convenient way to organize all the items in this problem. So we're going to make a chart with 2 rows and 3 columns so that we can put our formula as the headings, so the pieces of the formula as the headings of these columns. And specifically, we'll put rate times time equals distance. You could perhaps order those a little bit differently, like we have distance on the left in the way we wrote the formula initially, but it doesn't really matter. This is just kind of a standard way of doing it. So rate times time equals distance. We have a rate column, time column, and a distance column. And then we have 2 rows depending on the problem here. So in this one, it says a boat averages 18 miles per hour. It takes the same time to go. Okay, you can try to pick out what's going on, and notice that this boat is going downstream for part of the trip, and then it's going upstream for another part of the trip. So it's not as though we have 2 boats, and that's why we have 2 rows. This is just 2 different trips with the same boat. And so since we can label or distinguish those 2 trips, maybe we'll just label these 2 rows as up and down. And it doesn't matter which one you put on top or bottom, but we have those 2 distinct trips taking place, so we'll label our rows that way. Now, what we do know is what we'd like to fill in with this chart next. And it says in still water, a boat averages 18 miles per hour. Okay, and so we start to put the numbers from the problem into the chart, but notice the question being asked. It's always good to spot this, right? What is the rate of the water's current? So if that's the question being asked, that's what we have to answer, which means we would like a variable to represent that. So let's let C for current, although you could pick really a number of different letters for that. I'll just let C equal the water's current. And of course, we're talking about the speed of that current, so you could even specify that if you'd like, but we'll just say C is the water's current. Now, the way that water and current and boats work, which you don't have to be an expert sailor to know, is that when you're going with the current is actually pushing the boat in the direction that you are hoping to go. If you're going against the current, then it's the opposite. It's pushing against the boat, or slowing it down, you could say. Notice that we're given in the first sentence of this problem that in still water, okay, so in other words, if you ignore the current, then the boat averages 18 miles per hour. Okay, so if there was no current, that would be the rate up and downstream. Of course, there is a current which affects the rate of the boat, right? If you're going upstream, we said that's against the current, which means you're going slower. So you wouldn't be going 18, you'd be going 18 minus the current speed, or the speed of the current. So we'll use 18 minus c to represent the rate going upstream, which is against the current. Of course, downstream, which is with the current is pushing you. So you could say 18 plus c. You're adding the speed of the current to the speed of the boat, which is the 18. All right, so we have our rate table cells filled out, I guess you could say. Now let's move on to what else this problem gives us. It says it takes the same amount of time to travel 33 miles downstream. Okay, so let's start putting these things in here. We know the distance down is 33, as it just said, 33 miles downstream. And then if we keep reading with the current as 21 miles upstream, so the distance up would be 21. But notice it said same time, which means though we don't know what that time is, we can call the time of both up and down just t. Why don't we use t for time? All right, so this gives us a full chart, which is always a good step or phase to be in, but then we have to now turn the chart into an equation or two and try to solve the problem, right? The point here is to find the speed of the current, which we've now used the letter c to represent. Now, the way that a chart works in this case, of course, is just to hold the formula for us. We know rate times time is distance, and so we could get a couple different equations from these rows. If I take the top row, I can multiply its rate times its time to get the distance, which is exactly what the formula says. So I could write that as t times 18 minus c. That's just the product of the rate and time in that first row. And I know that equals 21, the distance. In the second row, we could do the same thing and get t times 18 plus c. Again, just rate times time in that row equals 33, the distance in that row. Now, we have two equations with two variables, which means we have more work to do. We have to somehow turn these equations into some kind of setup that would allow us to solve for ultimately c is our goal, right? The speed of the current. But we also have this t variable involved. Now, the way to go about this at this point may be unclear. You may think, well, what if I just distribute the t inside the parentheses in both cases? Okay, well, it's not illegal to do that. You could. But you're not going to end up with something that has a clear way to solve given the way we've solved systems of two equations and two variables so far. So what I'm going to recommend in this case is rather that we try to solve both of these equations for the same variable. What I mean is let's get the same variable alone in both equations. Now, you may say, well, which one? I see a t and I see a c in both equations. Okay, true. But if you just think through algebraically for a minute, it's actually easier to get the t alone with either equation because, for instance, look at the second row equation. If I just divide by 18 plus c on both sides, right, doing the algebra we know, then the 18 plus c's on the left side would cancel, leaving us with just a t over there, and that t would be equal to the right side, which is 33 over 18 plus c. So in other words, we've solved for t. We got t alone. Now notice we don't have it equal to a number because there's still a variable left over there. So we haven't figured out what the actual time was, but we got t alone. And the reason we were motivated to do that is because that was just a one-step job. Now look at the other equation and notice that we could do the same thing. If I divide by 18 minus c on both sides of that equation, then the 18 minus c's on the left side will cancel, leaving us with just a t, and then that's equal to 21 over 18 minus c. Okay, so a similar scenario is happening where we now have t alone in this first row equation, but it's equal to something that's not just a number, it has a variable left in it. Okay, well, the whole point is for us to try to solve for c ultimately. Let's not forget that. And at this point, I'm going to suggest we do something, which is, since we have both of these equations now solved for t, why don't we try equating the right sides of each of them, right? Because if t equals 33 over 18 plus c and t equals 21 over 18 minus c, then couldn't we say t equals itself and therefore those two expressions are equal? So we can say 33 over 18 plus c, which is t from the left equation in our screen here, must be equal to 21 over 18 minus c, which is what t equals in the other equation. Okay, well, what we've created here is a rational equation, which is the context of our work here, right? We know how to solve these at this point. To proceed to solve this one, we have actually a couple options. Since we have in our picture now, in this equation we've put together, what's technically called a proportion. Okay, a proportion is when you have one fraction equal to another fraction. And that's exactly what we have. With a proportion, you can use a certain strategy called cross multiply. So that's one option. Or you can use what we've also been doing, which is called clear fractions. They actually both accomplish the same thing, cross multiplying or clearing the fractions. But it's important to note that cross multiplying only works when you have a proportion. That is, when you have an equal sign between two fractions. If this were a plus or a minus between these two fractions, then we would not be cross multiplying. Clearing the fractions, of course, only works, as we've discussed, when you have an equation, which again is what we have, so that's why that's a valid option as well. Now, I'm going to demonstrate cross multiplication, since that's a perhaps less familiar method in this context, though I think preferred once students realize that it applies. Cross multiplication involves multiplying the diagonals of a proportion together to create a new equation. So if I take the diagonals of this proportion, again, this only works when you have a proportion which is an equal sign between two fractions. If I multiply the top left to bottom right, I'll maybe start with that one. That would give me 33 times 18 minus c. That's just multiplying those two items together. But then I set that diagonal product equal to the other diagonal product, which would be the 21 times the 18 plus c. All right, so what we have after doing that is an equation. Of course, notice this equation is looking good because it has only one variable, that is a c. And in fact, that's the variable we're trying to solve for. If you look above, we're trying to find the speed of the current, and we determined that c would be that variable representing it. At this point, we can use our familiar equation solving steps and distribute these two numbers to proceed. Doing this arithmetic will give us 594 minus 33c on the left side, distributing that 33 in the parentheses there. On the right side, we'll get 378 plus 21c. And from here, we'll just solve using our good old equation solving strategies. We'll go variables first, smaller to larger. And to do that, I'm going to add 33c to both sides. Combining those like terms as we do, that will give us 594 equals 378 plus 54c. And we're going to want to solve for c at this point, so we can subtract 378 from both sides. Let's see, we're a little bit out of space. Let's go over here. So 594 minus 378 should give us 216, and that will equal the right side, which now is just the 54c. Of course, if we divide by 54 at this point on both sides, then we get c equals 4. 216 divided by 54 is 4. So if you think back through where we started and where we've ended at this point, we were trying to find the speed of the water's current. We let c be that variable. We filled our distance, rate, time chart to create a couple equations, put those equations together in a way that allowed us to solve with cross multiplication. But we could have used clearing the fractions. It would accomplish the same task. And ultimately, we ended up with c equal to 4. So we can interpret that into an answer and say the speed of the current would be 4, and then our units would be miles per hour, given the context above. Let's try another example. This one starts by saying, suppose you drive 90 miles along the coast and then take a 5-mile run along a hiking trail. Your driving rate is 9 times that of your running rate. If the total time for driving and running is 3 hours, find the average rate driving and the average rate running. Okay, well remember, the first step to any word problem is to try to identify what kind of problem it is. As you can try to understand from what's given in this problem, notice there are some distances, the miles involved. There are some times, of course, the hours involved. And then the question involves the rate, right? Find the average rate. So this sounds, of course, like a distance equals rate times time kind of problem, which is the same type we just did in the previous problem. So we're going to go ahead and use the same strategy, which is let's go ahead and set up a chart, ideally with a couple rows and a few columns in it, because we can put our formula across the top, rate times time equals distance. Let's try to figure out in this problem why we have 2 rows. So this one says, suppose you drive 90 miles along the coast and then you take a 5-mile run along this hiking trail. Okay, so it's not like you're driving there and then driving back as if you have 2 trips. It's not like you're going with the current or against the current like we had in the previous problem. In this problem, you're actually taking 2 different modes of transportation. You have the running and you have the driving, right? So why don't we label our 2 rows exactly that? Let's say run, and let's just say dr for drive. All right, so we have running and we have driving. Again, doesn't matter which row you label which. Now, in this problem, we have to use what's given to start filling in the chart, right? Suppose you drive 90 miles along the coast, so they're just giving us a distance of driving right in that first little phrase there. 90 miles is what you're driving, so distance driving should be 90 along the coast, and then take a 5-mile run along the trail. Well, your run distance then would be 5. So that gives us a way to fill in the distance parts of this chart immediately, which is useful. Let's keep reading. Your driving rate is 9 times that of your running rate. Okay, so for the rate column in this chart, we have to turn that sentence into some kind of variable expressions to put here. So think, if your driving rate is 9 times that of your running rate, we could use R for the running rate, or you could use X or whatever else you'd like, but 9 times it would be driving, so we could say 9R for the driving rate. So let's go ahead and define these variables on the side so we don't get too lost without doing so here. We'll say let R equal the rate running. Now, when you're using a chart and labeling the chart itself with, run and drive and all those things, sometimes you can get away with saying, well, I'm labeling my variables in the chart. True, but it's good to be defining them as well, just to be super clear. So we have lowercase r here to represent the rate running, and then, of course, 9 times that, as specified in this problem, will represent the rate driving. That's why we have 9r in that rate place. Now, let's go ahead and think through the time. It says if the total time for driving and running is 3 hours. We have to turn that phrase into something with our time column. But notice what it said. The total time for both modes of transportation, running and driving, is 3 hours. So don't just go and throw a 3 in both time slots, because remember, 3 is the total time. Now, one way to understand that would be this. If we let one of the times be t, and the total has to be 3 hours, we could use the other, or represent the other time with the same variable by using 3 minus t. And the quick way to check that is, if I were to add these 2 expressions, t plus 3 minus t, add them up, combine like terms, and you'll get 3. And that has to be the total time, which is a good way to check that this actually does work. Sometimes students will get tripped up over whether to put t minus 3 or 3 minus t. Switching those can be detrimental to the problem, so make sure it does actually make sense in context. When you add up the time expressions, you should get a total of 3. All right, well, what this gives us is a full chart, which is a good step in the right direction. Now we have to turn this chart into some equations we can use to solve. Remember, we're trying to find the average rate driving and the average rate running, which, if you look at our chart, means we actually want to find r, lowercase r. That's used in both of those representations. Now, we're going to use the formula we have above our chart to turn these rows into some actual equations. So if we take the first row and use the formula with it, we're simply multiplying its rate times time, which would be lowercase r times t equals 5, the distance. If we do the same thing with the second row, that would be its rate, which is now 9 times the lowercase r, so 9r times the time, which is 3 minus t. We'll have to put that in parentheses since it's double or two terms. And we know that product is equal to 90, that distance. Putting these two equations together could involve a couple different options, but let's work on this simpler equation that we have, this RT equals 5. It would be pretty simple to solve that equation for one of those two variables by simply dividing by the other one on both sides, right? And then we could plug in what we get for that variable we choose to solve for to the other equation and solve from there. And there actually isn't only one way you could do this. You could solve for r or t. I'm going to choose to solve this one for t by dividing by r on both sides. Okay, so we're dividing by r on both sides of this first row equation. Now you may wonder why I would choose to do that. Again, this is not the only way to go about that, but I'm going to show you in a second why this would be a convenient choice. This will give us t equals 5 over r. Now, with that being a way that we've solved for t, I need to go plug that expression for t into the other equation we have. So I could rewrite that as 9r, and then open parenthesis, 3 minus, instead of t, I'm going to put the 5 over r that we just solved for t in its place, and then that's all equal to 90. Now the whole point may make some sense here why I wanted to solve that first equation for t, because when I replaced t in this second step here, notice now I'm left with an equation that only has r's in it, and in fact our goal is to find r. So if you took the other route and you had an equation with t's in it, it's not a big deal. You can still solve for t and then plug it back in. You know, as an equation like this that we got from the first row here to get r as well. So there are a couple different ways you could get through this. Now, with this equation we have, which is 9r, open parentheses, 3 minus 5 over r, close parentheses, equals 90. We want to solve this for r. We can do so by multiplying or distributing the 9r into both terms inside the parentheses. That will give us 27r minus, if we multiply 9r times 5 over r, the 9 times 5 would be 45. The r would cancel with the r down below. In other words, it'd be like 45r over r, but then those r's would cancel and just be gone. So really it's just 45 equals, and then we have 90 on the other side. So we have 27r minus 45 equals 90. And if we add 45 to both sides, just working on solving this equation for its only variable, which is now r, we get 27r equals 90 plus 45 would be 135. And if we finish that up by dividing by 27 on both sides, then we get lowercase r equals 135 divided by 27 is 5. Okay, so now let's keep in mind what we're doing, where we started, what our goal is. We've solved for lowercase r. Remember that that represents the running rate as we defined initially, and it's showing up, of course, in our table to represent the running rate, but also involved with the driving rate. And that's useful because the whole point of this problem is to find the average rate driving and the average rate running. So we could say, given that lowercase r is 5, the running rate would be then 5 miles per hour. That's just directly using the value of r, which we let be the running rate. Now, the driving rate, as we labeled in our chart, is 9 times lowercase r. So we could say, okay, fine, the driving rate of 9 times r would be 9 times 5, which of course is 45 miles per hour. And so now we've uncovered the rates of both running and driving from this problem, which was our goal. Let's try another example. This one reads as follows. A pool can be filled by one pipe in 3 hours and by a second pipe in 6 hours. How long will it take using both pipes to fill the pool? All right, so this, as you can probably suspect, is not a distance rate time problem. We've been dealing with those in recent examples, but notice there's no distance. There is a time, okay, it says hours, but there's no distance here. And so this is not a distance rate time problem. Rather, this is a perhaps new kind of problem or different kind of problem, and sometimes these are referred to as work problems because work is being done. In this case, these pipes are filling a pool. There are various types of these work problems out there. Sometimes people are washing a car together or, mowing a lawn together or whatever. They're doing some kind of work. And sometimes it's people, sometimes it's actual instruments like these pipes. But the point is, this is a work problem, and those have a standard way to set them up. Namely, we're going to say that work equals the number of jobs per time. Okay, that's going to be our ratio to use to understand how work works. Okay, so it's the jobs per time. If it's hours, it's the number of jobs per hour. If it's minutes, of course, number of jobs per minute. So in this case of a work problem, we have to understand in context what's given and put them together. Now, this has a pool being filled. So we could say, if we wanted to be descriptive like this, we could say pipe 1 is working with pipe 2. So we could say the pipe 1 work added with pipe 2 work is going to equal the total work. Now, this is not the only way to set up these problems, but I think this way makes some sense, and so I like to use it, but there are some other ways you could set up an equation to get through a problem like this involving the same information. But here's the deal. We're going to use the work ratio, the jobs per time that we've defined above here, to represent the work of these pipes that's being added together since they're working in the same direction to fill up this pool. So pipe 1, it doesn't really matter which one's which, but I'll just take pipe 1 to be the first one. It says a pool can be filled by one pipe in 3 hours. Okay, so the work ratio for pipe 1 we'll say is one job in 3 hours. We'll just call that 1 over 3, number of jobs over time. Now, we're going to add that with the work of pipe 2, which says a second pipe can do this in 6 hours. So one pool in 6 hours. So we have 1/3 plus 1/6. When you combine that work, which is why we're adding it, your total work is going to be hopefully one job, one pool in, we don't know how many hours, so we call it X hours or T or whatever variable you want to use. So we have 1/3 plus 1/6 equals 1 over X. And this is a way to set up a work problem that produces what you know, a rational equation. We know how to handle rational equations by clearing the fractions, and to do so we need an LCD. Of course, the LCD for 3, 6, and X would be 6X. And as you know, with clearing fractions, we're going to multiply that LCD by all these original terms. So I'm going to multiply the 1/3 by 6X. I'm going to multiply the 1/6 by 6X. And I'm going to multiply the 1 over X by 6X. All those original rational terms are all getting multiplied by the LCD of 6X. This is just clearing the fractions. Okay, as we go through to simplify this, in the first term we have 6 over 3 that would reduce to 2, but then we multiply by the x that we have there. So really it's 2x as the first term. The second one is 6x times 1/6. Well, those 6's would cancel, giving us just x. So we have 2x plus x equals, and on the right side the x's would cancel, giving us just 6 times 1, or 6. So we have 2x plus x equals 6. Of course, that means 3x equals 6. If we divide by 3 on both sides, then we end up with x equals 2. 6 over 3 is 2. And of course, in context, the 2 had the x value was the time for this total work, right? And that was the question being asked. How long would it take both pipes to fill the pool? So we could say 2 hours to fill the pool is what it would take.